Welcome back to my YouTube channel, and let's start the lecture 2 of PLL series. So in this lecture we will understand why we are using the low pass filter, okay, and some more about these other blocks. Okay, so let's consider there are two signals, okay, then V in we are giving when we are getting at output V out, and so let's consider that V in is your sinusoidal signal. So it is A in sine omega in t, and your V out is equal to A out sine or cos, whatever you want, you can consider cos omega out to out t. Okay, so now this is your PD. So in multiplier form we are making this PD. Okay, so what it will do, it will give V error. So V error will be equal to V in into V out. Okay, so it will be A in dot A out. Okay, and then sine omega in t cos omega out t. Okay, or you can say, you can do like this and you can use this formula. Okay, so V error will become A in dot A out by 2, then sine omega in plus omega out t plus sine omega in minus omega out t. Okay, so now there are let's take some cases. So the first case I'm taking, case 1, if omega in equal to omega and omega out equal to omega, what will happen? Okay, so your V error will be equal to A in A out by 2 into sine and then 2 omega t, okay, plus sine 0, which will be 0 only. Okay, so you are getting V error equal to A in A out by 2 sine 2 omega t. So there is no frequency error. Okay, no frequency error equal to 0, as well as phase error equal to 0. Okay, now let's take case number 2. In case 2, I'm keeping frequency error, that is del omega is not equal to 0, and I'm considering that phase error equal to 0. So for this, let's consider omega in equal to omega and omega out equal to omega minus del omega. So what is the phase error? Omega in minus omega out, so del omega is your phase error. Okay, so now you have omega and omega out. Okay, so let put it in equation. V error will become A in dot A out divided by 2, then sine. There was omega in plus omega out dot t, and plus sine omega in minus omega out dot t. Okay, so it will be A in A out by 2, then sine, and then this will be how much? 2 omega minus del omega t. Okay, so this will give omega, and this is omega minus del omega, and here it will be sine, this is omega, this is omega minus del omega, so it will become this will be cancel out, means omega plus del omega t, it will be cancel out. Okay, so this will be good. One more case, let's take. So in this case I'm considering phase error and no frequency error. Okay, so del omega equal to 0 and phi error equal to not equal to 0. Okay, so in this case omega in equal to omega out equal to omega, that is no phase frequency error, and there is a phase error, so we can say that phi in 0 minus phi out 0 equal to phase error 0. Okay, right? So what can we can use, put it in our equation of V error. So V error will equal to A in dot A out by 2. Okay, and then sine, then omega in plus omega out dot t, sorry, this small bracket, plus sine omega in minus omega out t. Okay, let's remove this. Yeah, now let's put omega in and omega out by 2 sine. This is see your if I'm looking your input signal V in, it is equal to, in this case, specifically in this case I'm saying V in equal to A in dot sine, this is omega in, or you can say omega, let's take omega, then it is phi in 0, it is shifted with this phase phi in, and your this v out is equal to sine omega plus phi in 0. Okay, sorry, phi out, this is phi out. So let's do it. So it will become, we have to multiply these two. Okay, after multiplying these two, what you will got, you will got 2 omega here, and then phi in 0, phi out 0. Okay, one component, and then second will be sine omega plus phi in 0 minus omega minus 0, right? Because we have to remove uh, this thing output, this from this. Okay, this is d, this is d. Hope it is clear. So this will be cancel out, and your v error is equal to a in dot a out by 2, and this will be sine 2 omega plus phi in 0 plus phi out 0, and yeah, then sine, this is phi in 0 minus phi out 0, but I call it, this is phi error. So it is phi error 0. Okay, let's go to the next slide. Okay, so let me write again. V error equal to a in dot a out divided by 2, and then into sine 2 omega phi in 0, phi out 0. Okay, 0 means it is t equal to 0 time here. Okay, then there is plus sine, then phi error 0. So this is your V error. Okay, now so if we are drawing its frequency spectrum diagram, so how it will be? It will be like this. This is omega. Okay, this is V error. There are two components, one here and one is here. Okay, this is at 2 omega you are getting, see, 2 omega you are getting this, and at 0 you are getting this much. So omega equal to 0. Okay, so in this case we told, in this third case, we are talking about third case. So in third case we said that there is no frequency error. Then what PLL will do? Since there is no frequency error, so it will try to make phase error equal to 0. Okay, if there is a frequency error, first it will make your frequency error equal to 0, and then it will go to the phase error and try to make it 0. Okay, so since there is a frequency error is 0 in third case, so it will go and try to make phi error equal to 0. It will make phi error equal to 0, and PLL will be locked. Okay, so for this, do we require this first term, or we want to work according to this second term? Okay, so we want to work on the second. This term is not required, means this term, this is not required. So how can we remove it? Okay, so this is, if we are using some low pass filter, okay, whose 3 dB bandwidth is lesser than this 2 omega, then we can reject it. Okay, so let's, this is a your low pass filter. Okay, and this is omega 3 dB, so it is going outside from this. Okay, so this low pass filter will reject this, and it will pass this one easily. Okay, so that only we require. Okay, so this is the reason why we use low pass filter. Okay, so to remove this high frequency component, we required low pass filter. Okay, so now what will be the VC? VC will be sine, sorry, VC will be A in, A out by 2 into sine. Okay, VC is this. Now according to this, your output frequency will vary, and again it will go to the PD. Okay, it will go to the PD, that output frequency will go to the PD, it will complete omega in and omega out, and will give some V error. And it will do this thing up to that time. I mean, it will do that thing up to whenever you will got this phase error equal to 0. Okay, this is phi in and this is phi out. And when your phase error will equal to 0, then it will stop, and your PLL will be locked. Okay, so like this the PLL will work. Let me clear this. Okay, so I hope you all understood that why we used this low pass filter. Okay, so to remove this high frequency component, okay, high frequency component mean this thing we want to remove. Okay, so for this we are using low pass filter. Okay, so how you will change this omega phi out? Okay, maybe you are thinking that how you will change phi out if you are changing this VC. Okay, according to your phi error. See, VC is depending on your phi error. Okay, then how your phi out will change? Okay, let me tell you that omega out we saw already in first lecture. So omega out equal to free plus kvco dot vc. Okay, so this vc came here. According to the vc, this omega out will change. And what is omega free? Omega free is the free running frequency of your vco, and this is kvco is the gain of the vco. Okay, so what is phi out? Phi out is equal to, or you can say, okay, so phi out equal to this omega out. Okay, if your omega out is varying, it is increasing, then your phi out will increase. Okay, so what is the requirement? According to that, your vc will change, and according to that, your phi out will change, and it will make phase error equal to 0. Okay, so we are now we know the importance of low pass filter. Why do we require this low pass filter? Okay, so now let's go to the next slide and understand a bit more. Let me, we saw that our see, for phase error detector, we define average of VE V error in steady state. Okay, so what is the V error? Sorry, average of the V error. It will be A in dot A out by 2 sine phi error. Okay, why it is? See, we saw previously that V error is equal to A in A out by 2 sine 2 omega t plus phi in 0 plus phi out 0. Okay, then plus sine phi error that we saw. So when you will take average of this thing will become 0, right? And only this thing will be remaining. So that's why I'm saying phi error, average of phi error is equal to A in A out and sine phi error. Okay. So if I'm drawing this average of phi error, how it will be? It will be like this. Am I right? Okay. So if your phi error is constant, if it is constant, then your average of V error will be constant. Okay. If you are varying your phi error, then you will go to sinusoidal wave. Okay. So your V error is average of V error. You can see from here, it is non-linear of phase error, right? V error, average of V error is, oh, let me write, V error is, average of V error is non-linear function of phi error. Okay. Now, if I want to calculate the gain of this V error, how we will calculate? Sorry, this is KPD equal to, we have to take differentiation of it, right? So it will be phi error. Like this only we can take, right? So this will be, this is gain. Okay. Now if we will see this thing which I'm going to tell you in detail in further lectures. So but for now, just I'm telling you, wait, if at phi error equal to 0, okay, you are giving some input phase, okay, some small change you are giving, by output will change. Okay, that gain, then what will be the gain, okay, of the PD? That gain is going to close to the value which you have at phi error equal to 0. This is small change you are giving. Okay, so what will be your phase error, that gain? Okay, so it's small change, so your gain will be, that KPD will be equal to the gain which is at phi error equal to 0 only. So what it will be? It will be A in A out by 2, right? This will be, because see, phi error equal to 0, you will put 0 here, and then it will become 1. Okay, so it is A in A out by 2. So now in second case, if we are considering that your P, see, at your PLL is locked at pi by 4, when your phi error equal to pi by 4, then the gain of the PDA will be different. Okay, so what you are doing at phi r equal to pi by 4, your PLL slope to be considered. Okay, now you are giving some change in input phase, a very small change. Okay, and then you will check what will be your KPD. Okay, that time your KPD will be different. Okay, so what will be your KPD? KPD will be equal to phi r equal to pi by 4. Okay, so it is different from this. Okay, so what it will be? It will be A in, A out by 2 and then cos pi by 4. Cos pi by 4 is 1 by root 2. So it will be A in, A out by 2 root 2. So this is your KPD. When your PLL is locked at phi error equal to pi by 4. And when it is locked at 0, it was A in dot A out by 2. So you can see that there is change in gain of PD. Okay, there is change in gain of the PD. So why there is the change in KPD? This is because this V error, I mean average of the V error is non-linear to the phase error. Okay, so I'm again repeating, in the locked state, if you make any change in the input phase, then you will see the gain by which voltage error will going to change is going to be different. Okay, since it is not linear, that's why this is happening. Okay, I'm writing. Okay, so in locked state, anywhere the PLL can be locked. Okay, so if you make any change in the input, okay, input phase, then you will see the gain by which V error will going to change, will be different. Okay, see we saw na, that KPD is equal to that was uh, V error by, okay, and it was equal to, okay, since it is not linear, that's why this is happening. Okay, now what is next? So now let's go to the block wise. Okay, so the PD we will try to make all block in terms of the we will change it with the S domain. Okay, by using the Laplace transform. So low filter. Okay, let's take a low filter. How can you make the low pass filter? Okay, low filter is low pass filter. So firstly, you can make it using the RC circuit. Okay, this is VC, this is VR, this is R, this is C. So what will be the transfer function? Transfer function will be, okay, so it will be what? It will be 1 by 1 plus SRC. So you can change it 1 by CS, and this is R only. So now you can calculate VC will be equal to V error into 1 by CS divided by R plus 1 by CS. And then when you will solve it, you will get this. Okay, so what is your 3 dB frequency? 3 dB frequency will be equal to 1 by RC. Okay, so that, okay, if you will compare with it, you will got 3 dB frequency. Okay, so we saw that V error was like this, the frequency spectrum. Okay, this was 2 omega, this was 0, this was omega. Okay, so we want to remove it. So if omega 3 dB is less than 2 omega, okay, so what will happen? You mean, I'm saying like this. If it is like this, so it won't reject this, it will reject this 2 omega. Okay, so it is good. And if your 3 dB is greater than 2 omega, then what will happen? It won't reject this 2 omega, and then the issues will come. So we have to choose R and C value of the low pass filter in such a way that omega 3 dB is less than 2 omega. Okay, then only it would be able to pass this or reject this, and we can look our PLL. Okay, so this is loop filter, and this is VCS, and there VRRS. Okay, now there is VCO. So how to write VCO? Let's see this also. Okay, so we know that for VCO, oh sorry, yeah, for VCO, we know that omega out equal to omega free plus k VCO dot VC. Okay, so phi out equal to omega out dot dt. But we can say, we can put this equation here. Okay, so it will be omega free dot dt kvco vc dt. So it will be equal to omega free t dot kvco integration vc dt. Okay, now what will be the del phi out? Okay, so del phi out will be kvco dot vc phi out minus, sorry, this is dt, minus omega free t plus kvco, and here the vc is, okay. Okay, so what it will be, it will be omega free t plus kvco integration vc dt. By this will be cancelled, so remove this, and by this and this will be cancelled. So you will, what will be remaining, the remaining terms are yeah, kvco del vc dt integration. Okay, this is the remaining thing. So I'm saying that del phi out equal to kvco del vc dt we have found the remaining. Now convert into in s domain, so it will be kvco by s del vc. Yeah, this is. Now this thing will go there, so del phi out divided by del vc equal to kvco by s. So see, this one is del phi out, okay, or you can say omega out, whatever. So phase it is, output phase. So what it will be kvco by s. See, this is del phi out, and there you have delta vs. Okay, so there it will come kvco by s. Okay, so let's make diagram again in s domain. So it will be, wait, okay, hmm, LFS, this is VLS, this is VCS, yes, and this is, okay, this is del phi in this. Okay, so this is your block diagram of PLL in S domain. Okay, this is all for today, and let's see what we have learned in this lecture. So the first thing, we understood that why low pass filter. Number two, we got to know that we converted PLL block diagram in S domain. And third thing, we understood that variation of KPD, that is gain of PD, okay, due to non-linearity, okay, that is VPD bar non-linear function of fire, okay, due to non-linear function in locked PL, or you can say when PLL is locked. So three things we understood: why low pass filter, converted PLL block diagram in S domain, okay, variation of KPD due to non-linearity, means the non-linearity of VPD average with respect to phi error when the PLL is in locked state. Okay, so that's all for today. Thanks, hope you like this lecture. In next lecture we will go in more detail. So thanks all, bye, let's meet you in next lecture.